really old guy some really old guy that's a lot smarter than me. Basically what happens here is this value of E is an approximation. It's still, it's a non-repeating decimal, just like pi is. And the way that you get this value of E, so let me do this, just used it. This value of E is equal to, bless you, as n gets infinitely larger and larger and larger, the value it's approaching is that 2.7 and change. Yeah. You like that? So what we use this value of E for is, there's a button on your calculator. It works the same as works with exponential growth, exponential decay. It models itself off of those. It's used a lot of times in equations. You'll see it follow the same pattern as a variable, as an x, which means it follows the same rules as exponent rules. You can multiply it to other numbers and do stuff like that. We will use it more when we're solving stuff with logarithms and natural logs. It's an inverse of stuff like that. It is a very simple thing to use. What we're going to look at today is just working through a few of the properties, graphing it, which means I can't take your calculator away from you because of the approximations, and then the solving it with the interest style problems. Once again, it is unbelievably simple to use. So let's put our phones away, and let's do this. Now we just. What we're going to do, like I said right off the bat, is just to do some very simple simplifyings with ease. We're using it as same thing as exponent rules we did in the past. You could, when you're simplifying these things, you treat it like you would a variable. So e cubed times e to the fourth is what? That's all it is.
So you just leave it as a variable?
Yes, ma'am. That's it. I mean, we're treating it the same way. And when we get into, when you see how it works with growth and decay style problems, you see how.
I like this chapter.
Most people do. It's not a very difficult chapter. What's the next one?
2e.
Or not 2e, that's the question.
Do that one just.
Yeah, I'm not very smart. And the last one, what do you have to do?
Oh boy.
9e to the negative 8x.
Perfect. So it's 9e to the negative 8x.
And then you have
9e to the 9 over
9
e
not
to the 8x.
Good. Yeah, whenever you're simplifying, whenever you're simplifying these, you have to have positive variables.
The exponents in the down.
That's fine.
Wait, so this is going to be on our quiz?
Yeah.
Okay.
So, we were talking about this last hour. When you'll see how the difference is for when you have to simplify versus graphing. When you go to graph an exponential problem, it'll just be written with a negative exponent, and you leave it in a negative exponent. When you go to simplify it, you have to have a positive exponent. Okay? You don't have to do anything to it. And as we get into it, I'll show you how you work it. Like I said, you'll notice there's not a lot of fractional exponents. There's nothing real crazy there. There is one other style that I want to show you just to remind you of what you do.
I've never understood this and I know.
Yes, you will.
I don't get it.
You'll always understand.
I've gone over it so many times
It's
and I just
6,
can't.
2x on the outside.
They should have square root of 36. Is it 6?
Yep.
2x?
It is.
And then e to the 2x inside.
Wait, see.
Or no, just e to the 2x, yeah.
You're done.
Well, because you just square root lower.
Whoa.
But like, what if it's like 5x?
Then you do your power rule again.
Well, it's something where you like pull it out and like leave it.
I don't think you see very many of them where you have to worry about the odds, where you had to do that. The ones that I've come across are usually where they work out cleanly.
Like that?
If you're worried about something like this, where it's the cube root of x to the 5th, y to the 6th,
I just
That
Z to the
hurts
8th.
my
I
head.
just like accepted that I didn't get it and I just
Well, one last time then. 3 goes into 5, how many times?
Once.
How many are left over?
2.
3 goes into 6, how many times?
2.
Any left over?
No.
3 goes into 8, how many times?
Twice.
How many left over?
2.
That's kind of easy with that.
Yeah,
Come on.
exactly. That's a great 3.
Thanks.
Amazing.
Don't
Okay.
worry, guys, I get it now, so I won't get it wrong.
You'll forget about it by tomorrow.
That's great. I'm glad you told me.
Oh no, if I ask you to approximate, what do you do?
Use a calculator.
Where's E at?
E is at the division symbol, second divide.
Second divide.
Yeah.
7.38,
Remember, all you have to do here is you're pressing buttons.
Equals MC squared.
That's the different E.
Yeah, that's it.
What are you doing?
She's dancing.
She's like break dancing.
Change. All right.
District.
So,
What does that do?
the question that we had up here a second ago was, why was the E value, let's see, it's 2e to the 3x. Okay, I get it. I know I'm never going to show that video again. I get it. It's annoying. It's stuck in your heads.
Well, now the actual song is stuck in my head.
If I'm looking at this versus what our exponential growth model looked like,
Oh, it's here too.
what's different?
There's just A is 2 and we in front of it and then E is 3.
That's about it. What's going to happen here when we go to graph these things, this value of graphing the exponentials, they mirror exponential growth versus exponential decay. They follow the same rules. Where do you think your y-intercept is going to be for this one?
2.
It's at 2. Okay. Your y-intercept would be at 2. Now, would this one match? I'm sorry, what? Dun, dun, dun. Now, what'll happen here is, yes, you're going to have a y-intercept at 2. Think about why that is. What if x is 0? What's e to the 2 times 0? 1. That's why your intercept is at 2. Okay? It's the same pattern of exponential growth or exponential decay. The only difference is how you tell which one is which.
The 1 has an E.
Basically, it's a lot of this words that means just this.
I love it when you do that.
I try. Why not make it as easy as possible for you guys to understand the differences? When you're dealing with exponential, there are these E graphs. They mirror the exact same thing as exponential growth or exponential decay, which we did earlier this week, which you guys did really well at because it was pretty easy. Those were more work than these will be. The reason that the exponential growth and decay problems are more work is because I made you do them by hand. You had to come up with your -2, -1, 0, 1s and 2s, put your parent function in, worry about your fractional exponents, and flip things around. When you're dealing with these, when you have that E value, that value of E is such a weird number. There's no nice, clean version of doing it. Really, the only one true point you're going to be able to give me on these graphs is going to be your y-intercept of your parent function, and therefore its shift. Any other points would have to be found via the calculator. You should never, ever, ever get any E graph wrong, because you have to have a calculator to do it. Okay? You mentioned this earlier, Christian, about your asymptotes. The rules for your asymptotes still hold true. Your parent function for these things are always going to have an asymptote where? Is it x equal or y equals 0? Y equals 0. When we throw in an h and a k, what do you think is going to happen? It's going to shift left and right or up and down. All right. Now, your exponential growth, remember what those two graphs can look like. Your exponential growth looked like going up like this or down like that. How were you able to tell which one it was going to look like? Kind of the first value. If A is positive or negative, good.
So if it's positive,
Yep. If it's positive, it's going up. If it's negative, it's going down. It's exactly the same. It's exactly the same thing.
What do you do with R? Oh, you just put that all in your
Yeah.
calculator, including the R?
Yeah, let me show you. Because your rate values are going to be given. For example, something like this. If I have y equals 2 times e to the 0.75x, I know right off the bat that my a value is what? Is 2. My r is 0.75. Is it positive or negative? So it's increasing, so I know it's got to do this. Is there an h or a k?
No.
No, so where's your only asymptote?
Zero.
So I know that's got to be there. Where's my y-intercept? 2. Then, to get me the secondary point to know how fast something is increasing or increasing, because we know it's got to be increasing, you have to put it in your calculator. You have to.
Wait, do you want us to test for try it out?
No, all I want you to do is go to your table.
So, okay,
Okay. I mean, I can make it more complicated for
I
you.
guess you wouldn't know either way.
So I'm going to put 2 e to the 0.75x, and I go right to my table. We'll bring it back down. So we knew it was at 0 and 2. The next one is at 2 and, or 4, or 1 and 4.2, 2 and almost 9.
So you can just like approximate.
So it's to be this.
That's great.
That's really it. Because now on a test or a quiz, being the fact that you have to use your calculator to give me that second point, you cannot calculate. I mean, you could if you want, but I don't know who would want to try and raise some crummy decimal to an exponent and multiply it all out by hand. You have to be able to tell me y-intercepts, what direction is the graph going, where's your asymptote, and stuff like that. It is extraordinarily simple to work with. Right? A lot less work. Now, what changes when you throw in a shift? What's up, man? What's up, bud? You still have to pull, yeah, you still do your parent function. Okay? So, what's going to be my parent function for this, for a shift? Yep, so my parent function is y equals 1 times e to the negative 0.5x. That'll be my parent function. We're doing this today? Yeah. Fun. It's a lot easier. Anyway, you won't believe me. So my parent function is that. So where's your y-intercept? It's at 1. Is this increasing or decreasing? Or excuse me, decay, is this exponential growth or decay? And why is it decay? Negative. Because your rate's negative. Okay? So is it going to be going dipping down to the right or is it going to be dipping down to the left?
Down to the right.
Remember, growth, when we did our growth stuff, your growth ones were going this direction or that direction.
Yes.
Decays were going this way
What?
or this way.
I found one of those.
I thought it was like completely flip one.
No, he just wrote it differently.
Okay. So on the right is growth, on the left.
Should you get it wrong?
No, the one on the right.
You just put in your calculator.
Right. Right. So I don't think I did it wrong. What was it? 1.
1 times e
So e to the
negative
negative
1/2.
0.5. Yes, it is. Well, here.
Oh.
My window. I was messing with my window for a different problem.
It's going like this.
What do you do? Your parent function first?
Yep.
Pi max.
So is that the parent function?
That's my parent function.
Okay.
So my parent function, we know that we had a y-intercept at 1. Right, because that was your a value. But you also go to the graph then to figure out the secondary point. Well, my secondary point, if I'm using... Yeah, you didn't remember that?
No, I didn't.
negative 1.6, negative 1 and 1.6. So your parent function is going this.
All right. Shoot them down. Wait, that doesn't move.
I'm sorry, what doesn't move?
The X.
My parent function asymptote always goes through 0. Will always be y equals 0.
Oh, you
Yes, ma'am?
haven't drawn other one yet? Okay.
Just kidding. All right. So now, when you have your shift, still your H's and K's. Guys, there's 15 or 16 of you here. I shouldn't have to talk over you. This is ridiculous. Which way is it going? Is it going to go right or left to?
It's going to go
Right to
left
one.
to, no, I think I got minus H. So it's just 2.
Oh, yeah.
Right to,
Kind of weird parameters set.
right to.
Is it right or left? I'm sorry, I was answering right. It's going to go right and then up. Because it matches the same pattern of your x minus h plus k. So each of these points then just has to go to the right 2, up 1. Now it's a solid line. And now where's my new asymptote? 1.
So the
What's-
asymptote just depends on K.
So your k value.
Really.
Which reminds me, what's your domain and range?
I mean, it's all real. And then
All
and
real?
Y has to be greater than 1.
There you go.
Why is everybody talking so much?
Because we want to get our point across.
Why don't you just supposed to write and everybody else okay?
Because you have raised the next one linear. Yeah. That's weird.
How about this?
All right, now it's fine. Now it's raising the next one up there. I don't know why don't know why you switched over. So you'll still have to do domain and range off these. Graphing of these is ridiculously easy, okay? Because you have to have a calculator to plot out that secondary point. You okay?
Yeah.
All right.
I think we're good.
I swear.
What's that?
I said I think we're good.
So it's just.
So now let's throw the weirdness then.
Pert.
So this is where the PERT stuff comes in. When we did our compounding interest problems yesterday, we talked about the amount of times something was compounding within a calendar year. We talked about it where it would compound quarterly, daily, semi-annually, or whatever. That was that value of n. Well, now when they change this up to a continuously compounding, what basically this means is that your money is always earning money. It's not calculated on specific time slots. But it depends upon your investments and stuff like that. It may be your favorite, it may not be your favorite. It all comes with knowing what you're doing to get your best bang for your buck. No, because you asked me earlier, could you use this to figure out how to invest stuff? I said, yes, this is helpful. I wasn't saying that you don't know what you're doing. I'm sorry.
She has no idea what she's doing.
I know, anyway. So what happens here is that you set these up identically to what we were doing the other day. The only difference is in the wording. The wording for these things, you're going to say you're compounding continuously as opposed to compounding quarterly, annually, or something like that. Okay? So if you hear the value continuous, you're using this, PERT. It's not because you have dandruff, it's just because you're using compounding continuously.
Yes.
This is very nice.
Wait, is that?
So-
In ours, the second word.
Yeah, they said this last hour too, they can't read my handwriting. This is your percent as a decimal. So Christian, 12% is? 0.12.
Yeah.
When you set these things up, Your overall amount is your A value, what you get after your investment is done. P is your principal, is your initial amount you're investing. R is your rate, T is your time. It's generally in years. Okay? Let me show you an example. Is your amount, how much will be in the account when you're done. So in this example here, if I'm going to deposit $1,000 in an account that pays 8% annual interest that's compounded continuously, what is the balance after, we'll do 20 years.
Yeah, now we're talking. Like,
Okay. So what is your initial amount that you're investing? So your P value is 1,000. Your rate is 8%. So what's that as a decimal?
0.08.
And how long are you investing?
20 años.
Okay, bueno. Necesito un calculadora para el matemáticos problema.
C.
Did you say C, Frito?
No, he said C.
I thought he said C, Frito. Hey, that's funny. All right. You just go right to your calculator, press enter. Yes, ma'am.
Isn't it supposed to be point
I didn't put it zero. Yeah.
I was doing that to make sure that Christian was paying attention. Do as I say, not as I do.
4,000. Wow. Oh, it is 20 years.
So over 20 years' time, what are you guys getting?
4,953.032424.
Wow. Wait, yeah.
What?
Yeah, wow.
Less rapido, por favor.
5,553.
0.03.
I don't know. Gracias.
Cállate. And
This one time, Mom had to do a skit.
Okay. Now, just like we did yesterday, they might ask you if you want 10 grand after how many years you get to figure it
Yeah,
out.
I do.
You just have to work your way backwards.
And it's likely to bank for how many years?
It would probably be like $6,000.
It can also be used to work with just population model. What's that? Nah, there's no reason to. There really isn't. And I would explain to you what you can do with this, because I want you guys to be able to go through a problem like this and use the calculator. All right? There's no reason for you to graph 119.6 as a y-intercept. There's no reason for you to try to calculate your ordered pairs to see where it's going to wind up in meat. Okay? There's a button on the calculator that says table. Yes, ma'am?
So we're not doing any like graphs for these problems on the quiz.
Correct.
It'll be the graphs for like the first section that we do.
Now, if I'm looking at this here, it says for the years 72 to 98, the number of species can be modeled by blank, where T is your number of years since 72. So what if T is equal to 0, that's your first year. What's the first year? So what's your initial amount then? So it's 119.6. Now they're talking about species. Can you have a 0.6 of a species?
Yeah.
No, so we'll say there's about 120 endangered animals. Okay? Does that make sense?
Yeah.
Okay. Now, when you go through that since that is your year 0, every year after that is just adding your T value.
Wait, T equals 26.
Excuse me. For what?
Because that's like 119.6e to the year decimal T.
Mhm.
But then at the bottom it says T is the number of years since 1972, and this is for the years 1972 to 1998.
Okay.
So wouldn't it be that amount of time?
I see what you're saying. What they're looking at is that this model is from that year's span. It's not saying that the T value is 26. Okay? You can say that after 26 years, you could have that many endangered species. Okay? I think you're overthinking it. Because now what I'm going to say is you put this function in your calculator, If the shoe fits.
You're supposed to say you should walk somewhere and Claire, you're wrong, Claire, you're right.
0.0917.
He does not care.
0.09163.2.
You go back to your table.
9-1.
In the table then, they're asking you approximately after how many years would this model say that there's about 1,000 endangered species if it continues on this.
About 95 minutes.
Well, actually, the year 95. 95.
Yeah, somewhere around. Oops. So between 23 and 24 years. Okay. So after you could say, and this is where it gets to be fuzzy. I would say between 23 and 24 years would be my answer because I'm not looking for a specific date, like Leafwood. I'm just sitting there looking at it approximately when did this occur.
So if we're like really close on a quiz, like the right area of approximation, like you'll get.
If it goes into something like this, what I would suggest that you write when it says approximately when the number of endangered species reached 1,000, I would say with this data that I have here, between 23 and 24 years.
So we just say between.
I'd say between 23 and 24 years. Now, there is one other way of doing this to get you to be a little bit more precise. Yes, ma'am?
Would you be okay if we said like between like the actual years?
Yeah, it's the same thing. Same thing in my head. To me, it's the same thing. Now, if you wanted to be more precise, think of it this way. You've got this exponential growth model going this way, and you want it to intersect 1,000, correct?
Yes.
So if you plotted this in a graph, you could find that intersection point. That's why I had my window all funky a second ago.
Oh, so it'd be like, oh, you put like.
Yeah. It was 23. This will give you the actual, if you change your window
What's your
around.
table and you look for y equals
Yes.
1,000?
So what I'm going to do here is I know that it's going to occur after 23. So I'm going to change my x maximum to 30.
Make it 20.
And then I'm going to make my y maximum, the height one, at 1,100 because I know it's got to go to 1,000 here. This is why I was messing with it, because I looked at my table to go through here, but the only thing I don't have in my graph now is that y equals 1,000 horizontal line. So I'm looking for the intersection. So if I graph those two, you're gonna get a better approximation of an exact time frame. Do you guys remember how to do the calculate intersect? Second, trace, number 5, and just hit enter 3 times. I changed it. So I'm getting an intersection. I'm getting an intersection after 23.158 years. So that's, it is, about, I just did this a minute ago. 158 and change as far as years is about 57 days. So 57 days into the year is what? There's 31 plus 26 is February 26th?
February 26th. Yeah.
So on February 26th of some year, 1995, February 26th, that's when you approximately hit 1,000. So if you want to be that super nerdy specific, go for it. It's kind of fun. Okay. Do those. Please and thank you.
No.
Fine, then don't do those.
Kidding. I mean,
Who does it really affect for this?
I have an A+ in this class right now.
Yeah, I'm pretty sure that's
everyone
stop.
has
Yeah,
an
an
A+.
not everyone.
I probably.
How do you really feel about that?
What?
How?
I feel great.
Snoop Dogg.
Yeah.
Hold on, wait.